More than 2,000 years ago, on the volcanic coastline of the Bay of Naples, Roman engineers poured a mixture of ash, lime, and seawater into wooden molds and created something that should not exist. That mixture became concrete, and today, while modern concrete structures crumble and crack within 50 to 100 years, Roman harbors, domes, and seawalls still stand, some of them submerged in the ocean for 2 millennia, growing stronger with time instead of weaker. Modern engineers, chemists, and material scientists have spent decades trying to understand exactly how this was possible, and only in the last few years have they finally begun to crack the code. This is the story of Roman concrete, one of the most astonishing feats of ancient engineering ever discovered, and the story of why an empire that fell more than 1,500 years ago still holds secrets that could change the future of modern construction. Cinematic drone footage of the Roman Pantheon, its massive unreinforced concrete dome glowing under soft light. Picture the Pantheon in Rome, a building constructed nearly 2,000 years ago, its dome the largest unreinforced concrete dome ever built, still standing today without a single crack in its structural integrity. Picture the harbors of Caesarea in modern-day Israel, where massive concrete breakwaters were poured directly into the sea, hardening underwater in conditions that would destroy modern concrete within a few short years. How did a civilization without modern chemistry, without power tools, without any understanding of molecular structures, create a building material so durable that it has outlasted almost every other man-made structure in history? The answer lies in a combination of natural volcanic materials, brilliant empirical engineering, and a chemical reaction that modern science is only now beginning to fully understand. To understand why Roman concrete became one of the most important technologies in human history, we first need to understand the world that produced it. Rome, during the height of its power between the 1st century BCE and the 2nd century CE, was not simply a military empire. It was an engineering superpower. Roman leaders understood something that many empires before them had failed to grasp, that lasting power requires lasting infrastructure. Roads, aqueducts, bridges, harbors, temples, and public baths were not just symbols of prestige. They were the backbone of a civilization that stretched from Britain to North Africa, from Spain to the Middle East. To hold together an empire of that size, Rome needed a building material that was strong, adaptable, affordable, and available in massive quantities. Traditional cut stone construction, while impressive, was slow, expensive, and limited by the availability of skilled masons. Rome needed something faster and more versatile. That need gave birth to one of history's greatest engineering innovations. Historical illustration of ancient Roman builders working near Mount Vesuvius, volcanic ash being collected in baskets. The secret ingredient came from the earth itself. Along the Bay of Naples, close to the restless slopes of Mount Vesuvius, Roman builders discovered a special type of volcanic ash, known today as pozzolana, named after the town of Pozzuoli, where it was first used extensively. This volcanic ash, when mixed with lime and water, triggered a chemical reaction unlike anything seen in traditional mortar. Instead of simply drying and hardening the way modern Portland cement does, this Roman mixture underwent a process called pozzolanic reaction, in which the volcanic ash reacted chemically with lime to form incredibly strong and stable compounds. Roman engineers likely discovered this by accident at first, noticing that structures built with this specific ash mixture near Vesuvius were remarkably durable, especially when exposed to water. Over time, through trial, observation, and refinement, they transformed an accidental discovery into one of the most sophisticated building technologies of the ancient world. The engineering challenge Rome faced was not simply mixing ingredients together. It was understanding how to apply this material across an enormous range of construction projects, from underwater harbors to towering domes, each with entirely different structural demands. Roman builders developed different concrete formulas for different purposes. For structures exposed to seawater, they used a specific blend of volcanic ash, lime, and even chunks of volcanic rock, allowing the concrete to be poured directly into wooden forms submerged in the ocean, where it would harden underwater through a process that seemed almost impossible for the time. For land-based structures like the Pantheon, Roman engineers adjusted the density and composition of the concrete depending on the height of the structure, using heavier aggregate materials like basalt near the base and lighter materials like pumice near the top, reducing the overall weight of the dome without sacrificing strength. This layered engineering approach, adjusting material composition based on structural need, is a concept that mirrors modern engineering principles used in skyscraper design today. CGI reconstruction of Roman workers, pouring concrete into wooden formwork along a coastline, waves crashing against early harbor walls. Constructing Roman harbors required a level of logistical planning that still impresses modern engineers. Workers built wooden forms, sometimes double-walled to keep seawater from washing away the mixture before it hardened, then filled them with the volcanic concrete blend. As the mixture cured underwater, it began forming a rare mineral structure that modern researchers only identified in recent years, a mineral known as aluminous tobermorite, which is incredibly rare in nature and difficult to produce even in modern laboratories under normal conditions. This mineral formation, combined with another compound called phillipsite, created interlocking crystal structures that actually grew stronger over time as they were exposed to seawater, rather than weakening or eroding. This brings us to one of the most fascinating aspects of modern research into Roman concrete, the fact that its durability is not accidental, but the result of an active, ongoing chemical process. In studies conducted by researchers at the University of Utah, the Massachusetts Institute of Technology, and the U.S. Department of Energy's Lawrence Berkeley National Laboratory, scientists conducted detailed mineralogical and chemical analyses of ancient Roman marine concrete samples taken from harbors like Portus Cassanus and Baiae. Using advanced imaging techniques including electron microscopy and X-ray diffraction, researchers discovered that seawater flowing through microscopic cracks in the concrete triggered new mineral growth within those cracks, effectively healing the structure over time. In other words, Roman concrete used in marine environments was not simply resistant to water damage. It was designed, whether intentionally or through empirical trial and error, to actually benefit from long-term exposure to seawater. Engineering diagrams showing crystal formation inside ancient Roman concrete samples, the self-healing property stands in stark contrast to modern Portland cement, the standard concrete used in most contemporary construction. Modern concrete relies on a different chemical process, primarily the hydration of calcium silicates, which creates a dense but ultimately brittle structure. When cracks form in modern concrete, whether from weather exposure, structural stress, or reinforcing steel bars rusting and expanding internally, water infiltration typically accelerates deterioration rather than reversing it. This is one of the primary reasons why modern reinforced concrete structures, despite advanced engineering and quality control, often begin showing signs of serious degradation within 50 to 100 years, while Roman concrete structures, built with far more primitive tools and no scientific understanding of chemistry, have survived for 2,000 years and counting. Understanding why this difference exists required decades of scientific investigation. Marie Jackson, a geologist at the University of Utah who has spent years studying Roman concrete, led some of the most important breakthroughs in this field. Her research revealed that the specific volcanic ash used by Roman engineers contained a unique chemical composition that promoted long-term mineral growth rather than long-term decay. Modern concrete, by comparison, is engineered for rapid strength and short-term reliability, ideal for fast-paced construction projects, but not necessarily optimized for multi-century durability. This distinction reveals a profound difference in engineering philosophy between ancient and modern construction. Roman engineers were not simply trying to build something strong enough to last a human lifetime. They were building empires meant to last for centuries, and their engineering reflected that long-term vision. Archaeological footage of underwater harbor ruins near Caesarea, fish swimming through submerged Roman concrete blocks. Of course, no historical engineering marvel escapes the weight of myth and exaggeration, and Roman concrete is no exception. Popular legends often claim that Romans possessed a secret formula lost to history, or that their concrete was somehow magically superior to anything modern chemistry can produce. The reality, while still remarkable, is more grounded in observable materials science rather than ancient mysticism. Roman concrete was not magical. It was the product of specific environmental resources, particularly the volcanic geology of the Italian peninsula, combined with centuries of practical experimentation and engineering refinement. The volcanic ash used in the most famous Roman marine structures came from a very specific geological region, meaning that not all Roman concrete throughout the empire performed equally well. In regions without access to this specific volcanic ash, Roman builders used different formulas with varying levels of success, and some Roman concrete structures throughout history have indeed crumbled or required repair, particularly those built with lower quality materials or less careful construction techniques. Another common myth suggests that modern science has been completely unable to replicate Roman concrete until recent breakthroughs. In truth, modern engineers have understood the basic chemistry behind pozzolanic reactions for over a century, since volcanic ash-based cement was studied extensively during the 19th century industrial period. What modern science struggled to replicate was not the basic chemical reaction, but the specific long-term self-healing crystalline growth that occurs uniquely within Roman marine concrete formulations. This distinction matters because it separates verified scientific fact from popular exaggeration, allowing us to appreciate the genuine engineering brilliance of Roman construction without resorting to mythical explanations. Historical illustration of the Roman Forum during peak construction, workers, oxen, and cranes visible in the background, The engineering brilliance of Roman concrete extended far beyond material chemistry into logistics and labor organization, which is equally impressive when examined closely. Producing concrete on the scale required for Roman infrastructure meant organizing massive supply chains of volcanic ash, lime, water, and aggregate materials, often transported significant distances by ship and cart. Roman engineers developed standardized construction techniques that allowed relatively unskilled laborers, including soldiers and slaves, to participate in large-scale concrete construction projects under the supervision of skilled engineers and architects. This standardization dramatically increased construction speed compared to traditional stone masonry, allowing Rome to build roads, aqueducts, bridges, and public buildings at a pace that helped unify and control an empire spanning 3 continents. Roman aqueducts, for example, relied heavily on concrete construction techniques to create waterproof channels capable of transporting fresh water across enormous distances, sometimes stretching for more than 50 miles from mountain water sources to city centers. These aqueduct systems used precise engineering calculations involving gradual elevation changes, allowing water to flow steadily through gravity alone, without any mechanical pumps. The concrete lining used within these channels needed to remain watertight for centuries, another testament to the durability of Roman material engineering. Some sections of these ancient aqueduct systems remain structurally intact today, an achievement modern infrastructure planners still study when designing long-term water management systems in earthquake-prone or environmentally challenging regions. Drone footage of a preserved Roman aqueduct stretching across a green valley, still partially standing after 2,000 years. The legacy of Roman concrete extends far beyond the ancient world, influencing modern engineering in ways that many people never realize. During the Industrial Revolution, engineers rediscovered the principles behind volcanic ash-based cement, eventually leading to the development of modern Portland cement in the 19th century. While modern cement formulas differ chemically from ancient Roman mixtures, the foundational understanding of pozzolanic reactions directly traces back to Roman engineering discoveries. Today, researchers studying climate change and sustainable construction are once again turning to Roman concrete for inspiration, particularly because traditional Portland cement production is responsible for a significant percentage of global carbon dioxide emissions. Modern concrete production requires extremely high kiln temperatures to produce Portland cement, consuming enormous amounts of energy and releasing substantial greenhouse gases in the process. Roman concrete, by comparison, required significantly lower processing temperatures, since it relied on naturally occurring volcanic materials rather than industrially manufactured cement powder. This has led several modern research teams to explore the possibility of developing Roman-inspired concrete formulas that could reduce carbon emissions while simultaneously increasing structural lifespan, potentially solving 2 major challenges facing modern infrastructure at the same time: environmental sustainability and long-term durability. If successful, this ancient Roman innovation could directly influence how future skyscrapers, bridges, and coastal infrastructure are constructed, particularly in regions vulnerable to rising sea levels and increased storm activity due to climate change. It is a striking realization that a building technique developed nearly 2,000 years ago, using nothing more than volcanic ash, lime, and seawater, might hold solutions to some of the most pressing engineering challenges of the 21st century. CGI visualization, comparing a modern concrete seawall crumbling after 50 years next to a Roman harbor still intact after 2,000 years,